This is a video on the Bayesian tab in my Shiny app. I've added some things in the Shiny app specifically for working with posterior distributions. This doesn't run a model, but once you do have a Coda, which is from the Coda package, once you have your chains, then I think this could help to run a set of graphs and summary statistics that hopefully are going to be useful to your work. So let's begin. So right now we're looking at 5 different parts of the Bayesian tab. We have diagnostics. We have a way to examine posterior distributions. We have different types of posterior predictive checks. We have some graphs on hierarchical estimation, and we can calculate statistics for proportions greater than a certain value. And so we're going to go through each of these different categories, and we're going to finish with the case example. And I'm going to use, I would use all of those different 5 sections. Okay, so let's go to the Shiny app. I'll start it up. For most stuff, you can just use your chains, your posterior distribution. However, sometimes you do need to use the data, your data file that you used in that analysis. So we're going to begin with the support study, and that's from Frank Carroll at Vanderbilt. He's also a lot of his codes is used throughout this entire Shiny app, and for this demonstration, I'm going to use his support data, and I'll put in a link to his data sets as well as John Kruschke's Bayesian analysis blog. I'm using a lot of his data and a lot of his code for this for the Shiny app. So I've entered the support data frame name in the Model Builder tab, and I'm going to go to the Bayesian tab, and I'm going to put in my Coda object, and for the outcome we're going to look at, it's length of stay. And on this first section, under the title Run Diagnostics on the Parameters from the MCMC Simulations, we can select a parameter. We'll do that in box 1. And we'll just go ahead and begin with the first one, and that's the mean of our log y. In the likelihood that I'm using for the analysis, I'm using a log normal likelihood. With time and, say, cost, those are 2 very positively skewed outcomes. In this, we're looking at the mu of our log y value, but we also can back transform that value into the actual scale, which would be under days. So we can transform it back. We can get the mean, median, and mode for those values from that by using the log normal likelihood. And so, but we're just going to go ahead and begin with the very first parameter that we have, which is the mu of log y, and that's for our first group. We're using 8 disease groups, so I have 8 values per each of those types of parameters. We're going to click yes on Run the Diagnostics, and we see what comes up, and this will come up for any parameter that you enter, not just for this data set, but once you enter your data frame or your Coda object into that first box, then it'll generate all the parameters. So I'll just scroll down that list that I have this Coda object. And then you can just pick whichever one you want to look at. So for this very first one, we have 4 different graphs that come up. On the top left, we have trace plots for 4 chains. I think I ran 4 chains on this. It might be 3. On the top right, we have a graph of the autocorrelation. On the bottom left, we have our shrink factor or our Gelman-Rubin statistic. And on the bottom right, we have a density plot for the 4 different chains with the Monte Carlo standard error. So on that first graph on the top left, we see that we have our trace plots, and those will show us how our chains have traveled through that parameter space. And what we're hoping to see is that our 4 different chains overlap, and ideally they're not going to clump up in certain spaces or take a long time to move on to the next potential value. So what we're looking at right now is a good example of our different chains. They seem to overlap, which is a good sign of convergence. And they don't appear to kind of get stuck in a spot or take too long to move on to the next credible parameter space. So that looks pretty good, that we have a lot of overlap. And another way we can examine convergence is to look at our autocorrelation. We have that in our top right. And so our autocorrelation would indicate that correlation in our chains, in each step of the chains to the next step. So on the lag, that represents the how many spaces ahead that we have. So if we and ideally you'll have a value that's as close to 0 as possible. And so what we see here is by the time we get down to the second or even the third subsequent step, the 3 steps ahead, we don't have a lot of correlation. So we're seeing I guess you can say the walk through the chains. You're seeing it's traveling through a lot of different spaces, and it's trying to find the most credible parameters. So we don't want things to get stuck. We don't want a high correlation, because that means that our chains aren't traveling through the credible parameter spaces. And so with this lag close to 0, where you can see just a couple steps ahead, all the way down to about 30 or 35 steps further down, there's not much correlation. So that's another sign of convergence. And so on the top right of this section, we see the ESS. That's the effective sample size. Ideally, we will want to get over 10,000 for that. And so what the effective sample size is, it's the number of chains we have divided by our autocorrelation. So that's more or less, that's what it represents. So if that number is over 10,000, then we should feel pretty good about our effective sample size. That would indicate that we have a very high ratio of chains to autocorrelation. So the larger that number is, the better. And ideally, I think we'd probably want to hope for at least 10,000. So on the bottom left, we have our shrink factor statistic, or the Gelman-Rubin statistic. And so ideally, we'll want to have that value as close to 1. And that value represents the ratio of within chain variance and between chain variance for different steps. And so if we have a value of 1, that would indicate that there's that the chains are pretty much telling us the same thing. If we have a chain, or if we're having issues with our convergence, then we would end up with a bigger value. And the threshold for this is usually about 1.1. So hopefully we're going to have a shrink factor that is between 1 and 1.1. And that would indicate, again, the ratio between our within and between variance. And so we see that that value is well below that cutoff of 1.1. And so on the bottom right, we have our Monte Carlo standard error. And that would be the standard deviation of our mean for each of these different steps in our chains. It would be that standard deviation divided by the square root of the effective sample size, which we have up top on the top right. So if you're familiar with standard errors, you'll know that that's the general idea of a standard error would be your standard deviation divided by the square root of your sample size. So it's analogous to that. And what we can also see in these density plots are that these chains, the different, I have 4 chains. I think I at least have 3, and it looks like I have 4. But the more overlap we see with those chains on the bottom right and the trace plots on the top left, that gives us an idea that our simulations converged, our chains converged. So overall, these are good results for our diagnostics. And just to show how it works, we can go on to the next group. And you can see a high effective sample size, very similar statistics. Trace plots look about the same, and we can just go to the next one and it'll produce the same graphs for us. So let's go on to we're going to look at our posterior distributions, and we have them with highest density intervals. And we also have the option of producing ropes, which are regions of practical equivalence. And we can actually work with our settings. So above, for these graphs, we kind of just have a standard set of displays, but in this section, we're going to be able to examine our posterior distributions and modify our graphs to help give us our best view. So let's go ahead and I have the mu of log y showing, but we're going to go ahead and change that to the mu, or the mean of y. And that log value is transformed back to its original scale. So let's go ahead and do the first one. And that's in box 1. And we're just going to go down to box 19. Everything before that helps to modify that graph. We're going to click on yes. And this gives us a graph on our posterior distribution for the mean length of stay for that first group. And just to show us what a 95% highest density interval is, I'm going to go back to a different tab. I'm going to go back to my 95% confidence intervals. And let's see. I typed in the wrong data frame name. So let me correct that, and then we're going to have SLS for steady length of stay. We're going to put in our different disease groups. I'm just going to go ahead and run the confidence intervals. And these are the 95% confidence intervals that we always use with the frequentist approach. I'm just going to increase the label sizes so I can read a little bit better. Okay, so we have, for our length of stay, we can see, and I'm going to go ahead and read the names off really quick. The first group is, the abbreviation is ARF, MOSF, W, and the rest would be sepsis. It's not showing, but that is acute renal failure and multiple organ system failure with sepsis. So that's a really tough, that's a tough condition to deal with for everyone. It's maybe not surprisingly, it's going to be the one with the greatest or the longest duration in their hospital stay or their within the study, and that's about 25 days. Next we have COPD. Below that we have CHF. The fourth one is cirrhosis. Below that is coma. Then there's colon cancer, lung cancer, and multiple organ system failure with malignancy. So these are, in this support study, these are patients that are facing end-of-life conditions. So their outcomes in length of stay and cost can be on the more extreme side. But we're gonna go back to the Bayesian tab, and we're gonna compare ARF, MOSF, or I'm just gonna call it ARF, and we're gonna compare with COPD. And I'm just gonna increase so you can see the values on the right side more, on the right side of this graph. Okay, so range it, and then I'm going to switch that view by the value, and it can range from about 9 days to 25 days for these different eight different groups. Let's go back to the Bayesian tab. So right now we're looking at let me go back. Okay, so for ARF, it's about 24 days on the average length of stay. This is what we estimate from our Bayesian analysis. And so I do have the option of comparing parameters. Because we're working with that posterior, we have all of the credible values in that posterior, so we can make different group comparisons, and those would be valid estimates. So let's go ahead and compare ARF, and we're going to pull up the second disease group, which is COPD. And what we're looking at now is a difference of 10.8 days, so almost 11 days difference between that. So we may want to know, is that if we were testing, would we consider that if our null hypothesis is that there's no difference between the two, could we say that's true? Would we fail to reject the null hypothesis? And so what we can do is we can add in ropes. These, what I have listed above here, those are regions of practical equivalence. So, and that can help us with null hypothesis testing. We can state that for maybe there is a difference, maybe there isn't. There's probably a range where we can say that there's probably no difference between them. They can be off by a day or two, but we're not really too worried about a 1 day difference or a half day difference, or maybe even a 2 day difference. But what we can do now, that since we're working with the posterior distribution, we can set up kind of a range of values where if that difference exceeds that, then we would reject the null hypothesis that there's no difference between the two. But we actually do, in Bayesian analysis, we do have the option of accepting the null hypothesis. So if our 95% highest density interval falls outside of the rope, then we would reject the null hypothesis. if that 95% confidence interval, which in this data is 7.68 to 13.8, if that falls within that rope, then we would accept the null hypothesis. So let's go ahead and say maybe for our purposes, 5 days, give or take, is something where we would be concerned with. Is this something that we're going to have to maybe come up with different operational practices, different clinical approaches or procedures that we're going to have to do? So maybe we're going to say within, if these two or 5 different have a length of stay that's different by 5 days, maybe that's when we start to act differently, or maybe that's something we're really concerned with. So maybe that would be a substantial difference. So let's go down to question 7. Question 6 gives us the option to add a rope. We're going to do that in a second, but we have to come up with some rope values. So we're going to say a difference of 5. Since we're already looking at the difference between ARF and COPD, we want to have 0 as one of the values that we're going to test for. So we're going to have our rope 5 days less than 0, so that's -5. Our upper rope value will be 5. So we have a rope that goes between -5 and 5. We're going under the assumption that we don't have an idea yet of which group we think we're going to would be the one most likely to have that longer length of stay. And so I'm actually going to go down. It's further down, but at number 18 we can plot a comparative value. So I'm going to keep that as 0. I'm going to go ahead and go back to number 6. I'm going to add yes for adding the rope. I'm going to click yes on 17, and that's going to add the comparative value of 0, because we want to know if 0 is a credible value in our difference. If we're doing a frequentist test, that would be a value that we would definitely look at, and that would help us to determine statistical significance. So we're going to leave 0 as a comparative value. And so we're going to scroll down. And so these 2 red lines that are that surround this green vertical line, those 2 red lines are indicate our rope, and that green line in the center would indicate that comparative value of 0. So first of all, we can clearly see that because that 95% HDI, it exceeds, or it's outside of the rope, we can reject the null hypothesis that there is no difference between the two. And maybe even before that, we would want to see if 0 is a credible value for a difference between length of stay between our ARF patients and our COPD patients. So we see that that difference is clearly larger than 0 and clearly outside of that rope of 5 days, give or take. So we can see, and actually it's a little tough to view this because that red it's kind of harder to read the value. So I'm going to go up to box 13. I'm going to click yes, and the question is, should we show the curve instead? And so I put the curve in so that when you're working with these values, maybe it's harder to see that with the red background. It's a little bit easier. Maybe it's the color. So let me go back up to the color. And that's box 14. I'm going to change it to yellow. But I'm going to go ahead and turn the curve off and go back to the histogram. Okay, that's a lot of yellow. It's kind of bright, but maybe it's a little easier to see that the text there. But overall, we see that there's going to be a substantial difference between the length of stay for ARF and COPD patients. And if we're concerned about five days being too much of a difference to ignore, then we can use that rope to give us an idea that that is a big difference. And suppose there are people who thought, yes, that are not surprised that there is a 10-day difference. We can, and maybe they wanted to test. Maybe they felt very certain going into it that your ARF and patients with sepsis are going to have a much longer length of stay. Maybe they wanted to test to see if that difference is 10 days. So what we're going to do is we're going to change our rope, and we're going to put that around 5 days around that the value that they were interested in, which was 10 days. So we're going to put 5 days above and below that 10-day value. And we're going to put that comparative value back to 10, because that would be that middle value that maybe they were suspecting. So we see that the rope, within that rope, we have the 95% HDI for the difference between those two conditions on their length of stay. And we'd in this case, we accept the null hypothesis. That's one of the nice things about Bayesian analysis, that we can accept the null hypothesis when we're doing that here. Okay, so just a quick thing to show. So we have the text, our HDI text. Just going to scroll up a little bit. And you can see, if you want to move those upper and lower limits up, you can go up to box 16 and increase it, which spreads it out. Or if you don't have a lot of space for your graphing, then you can decrease it and it'll bring in those values closer together. We can increase the label sizes by going up to box 9. Maybe that's easier to display your results. We can add in a title in box 10. Box 11, we can label the x-axis. I guess we could put in density, but that's probably not too useful, so I'm going to take it out. So there's the main title. At the bottom we have our x-axis label, our y-axis label. Maybe we do want to show that curve instead, so we're going to change no to yes at box 13. I have x-axis limits, so maybe I'll just extend it to about 0 and 20 days. Okay, so that maybe this graph works, but and I don't have it in this example, but if we were working with the beta distribution in the likelihood, whenever I refer to a distribution, I'm always thinking about the likelihood and that formula or the model that we wrote prior to getting to this step. But in your model, if you used a beta distribution or a binomial distribution, I'm going to refer to beta for both beta and binomial. But if I had something like that, what I could do is I could calculate Jacob-Cohen's effect size statistics. And for example, if I was using a beta distribution that's for a small, medium, or large effect, that would be an effect size of 0.2, 0.5, and 0.8. So if I wanted to know is that difference, the difference between, say, 0.45 and 0.5 is about is a lot easier to see than it is between 0.95 and 1.0 or 0.05 and 0.00. So if you're in the middle on a for a binary outcome for that distribution that ranges from 0 to 1, it's a lot easier to move around in that middle area than it is on the extreme low and high end. So if you wanted something that's that puts that into perspective, you can use an effect size. Right now I just have it for the beta distribution, so I can't do an effect size here. I will at some point, but for right now we just have it for beta distributions. But that is an option that I'm not showing here. Okay, so now we're going to go on to the, we're going to look at posterior predictive checks. A lot of what I built here is for hierarchical estimation. Say if you're working in a public healthcare system and you have quite a few different hospitals in your system, what you can do is see what that overarching or that hierarchy that's that affects the tendencies of the lower level hospitals. So if you're in one big healthcare system in, say, California, and you have about 20 to 30, or actually you can have, you don't need, that's not a requirement to have 20 or 30, but an example, say you have 20 or 30, those 20 hospitals are probably, for certain outcomes or whatever that might be, they probably move in a similar direction as they go up and down, whatever that scale is, because of that hierarchy from that big system. And this could be anything. It could be in classrooms in a school district, or it could be later on we're going to see an example in baseball, but it could be players in certain positions. Maybe left fielders have a better batting average than pitchers. But any type of hierarchy that you think is important to consider, hierarchical estimation can help take that into consideration when giving estimates. So that posterior predictive check for groups, I'm putting a lot of focus on how to look at different groups. Okay, so for this we're going to look at, we're going to continue with the support study. We're going to look at length of stay, and we're going to do it for the posterior predictive check. It's at box 1. You have different options. You have it for a when using a normal likelihood, log normal, t distribution. This is kind of more if you're using, for this display, it's more if you're using like an ANOVA design, or maybe if you're just really only interested in certain groups. The display is going to look a little bit different than it could have been with under the normal or log normal. So for the t distribution, we're not doing a t-test. We're just using that. We're taking advantage of the shape of the t distribution, which has heavy tails, which means it can extend out further than the normal distribution, or it can do it in a way where we can take into account outliers. So with cost or time, that's very useful. And so I have something called an OLS, where we can't do an ordinary least squares calculation with a Bayesian analysis, but I'm using it as an analog to that, again with regards to my likelihood. So say if we're doing a regression model and we're looking at a linear trend between, say, the number of the family size and median income of families, and we want to see what that trend looks like, we can look at it as thinking of along the lines of polynomial terms. We can consider it like a linear, which is just that straight line. I have something that could also look at a quadratic trend or association. And so that's where we just square our x value, our predictor value. Say family size, we would just square that value and add that along with the linear term. And we can also do it for cubic. I don't have it for logistic yet, but I will put that in. I just put this in as a placeholder. So we can look at the distribution for these different groups, and we can also use, we can get the trend for any kind of linear trend line that we're working with, and I'm using a hierarchical estimation there as well. Okay, so we're just going to go with normal, and our outcomes in box 2 is length of stay. Our group variable would be our disease group. So at this point, I'm not gonna, for number 4, I'm gonna leave it as no for now. And so I can skip number 5. I'm gonna go to number 6, and I'm gonna bring up the overall, which would be the mean estimate based on those 8 groups. So we're thinking of, in this analysis, this mu of the overall y, that's the overarching distribution for those 8 groups. Because we're doing a hierarchical estimation, it is taking into account the differences between the groups and for each of the patients, but we're looking at the 8 groups there. So we're going to go ahead and put in our standard deviation parameter. So number 6, that would be our center, and number 7 would be our spread. We're not always going to work with the standard deviation. Depends on what distributions we're working with in our likelihood. Sometimes if we're working with the t-distribution, we have 3 different parameters that give us our distribution shape. So I'm going to go ahead and, for this case, I'm going to go down to sigma, which would be our standard deviation. It's just the written out name for that. And giving the sigma over for the overall. Number 8 is for when we're working with t-distributions. So we'll skip that. 9, 10, and 11 are for when we're working with trend lines. We'll leave our posterior lines the same, and I believe we can just skip all the rest of these and go straight down to 27. Click yes. Okay, so we have the we definitely have, so in blue we have our different we have histograms on our different length of stay times. The orange lines, those represent our estimate, or this is the posterior predictive check part. We generate different just different distribution lines. So we have in our different chains, we have thousands and thousands of rows, and so I randomly grabbed 20 rows of those data and calculated the posterior distribution shape for those. So I'm going to change that 20 to 50, and we're going to see that look a little bit different. And you can see with 50 distribution curves that it's a little easier to see those orange lines now. So we know with the normal distribution, it's going to stretch out below the value of 0. So I'm going to go ahead and go to box 21. And let's see, I'm going to go to about negative 100. Okay, so we can kind of see what could be an issue with our normal distribution. it's placing credible value over a range that doesn't exist. We don't have negative length of stay. We don't have negative days in that distribution. But because we're working with the normal distribution, we can see that it wants to provide estimates for an area that doesn't exist. And we can see that once you get past about 10 or 15, maybe 20 days, then we're starting to have a little bit more issue with those estimates. We're starting to see those orange lines kind of spread, or we're seeing less consistency. So it's not bad overall. That's a pretty good representation of it. We can improve it. So we can do that by going with the log normal distribution. Okay, so, but you can graph it. I'll show more on the graphing options. You can work with that normal distribution. And we're going to go back up. And we're going to go back to number 1. And we're going to use a log normal distribution. In box 1 and box 2 and 3, we're going to keep those the same, as well as 4 and 5. And we're going to go down to box 6. And we're going to use, for my data set, I named the that parameter as PRI, mean of log y, and I'm going to use the matching standard deviation, or the sigma, for that. And let's see, we'll skip 9, 10, 11. We'll leave 12 as the same 50. And I think we have that. Let's go ahead and take a look. So we can definitely, and I'm going to move that minimum value just over a little bit, just so you can see what that negative, those negative value spaces look like. So let's go back to negative 50. Okay, so it's just graphing on that orange you see on the bottom. It graphs, but it's at 0. But we can see that there's a lot more credible space in the right areas. So we see that that orange covers those blue actual data, the histogram, the blue histogram. We see a better coverage. So in this posterior predictive check, our predictions seem to match the data well. So that's a good sign. And we do see a little bit of scatter in these orange, the Bayesian estimated values. We see it spread a little bit more after about 20 days. So maybe we have something going on with our different disease groups. So what we're going to do next is we're going to compare those different groups. And that blue and orange looks okay, but I'm going to probably change that as well. So we're going to probably work with those middle boxes that we've kind of skimmed. So let's go back. We can leave the settings for the first 3 as the same. And we're going to go ahead and generate group levels in number 4. We're going to click yes. We're going to go to, and we see that the first group, ARF/MOSF with sepsis, or just ARF, we see that's the first one that comes up. And so what we're going to do is we're going to, since we're working with the log normal distribution, we're going to go up to mu of log y, and with 1. And we're going to go, so it's shifted over a little bit, but that's because it's step 7. We also need to put the sigma of log y. So we're going to select that parameter. Okay, so we see that that our estimates, the orange lines, have a much better fit on what we're seeing for our first group. So that's a pretty good fit. That's a pretty good estimate of that. I'm going to go ahead and make some changes to the appearance. I think I like 50 lines. So I'll leave it number 12 as is. Main title, I'm going to put estimate of LOS. Let's go to box 15. We're going to change the color. We'll go with blue, but we're going to use cyan instead. Okay, that helps to kind of see that a little bit better. That works better with the orange. I'm just going to increase this XY label sizes in box 18 so I can read the main title a little better. It's a lot of white space in the graph, so I'm going to change the limits on the x-axis from 0 to about, let's try 150. Okay. I'm going to move up in box 20, I'm going to move up the y-axis a little bit. I'm going to go 0 to about 0.05. Let's see. Okay, that looks good. So we're looking at density values, so probably good to start low with if you modify the y-axis limits in box 20. I think we can get rid of that negative 50 value and just leave it as 0. I just wanted to demonstrate that with the log normal likelihood we're going to get a distribution that makes sense. And let's see, I can add some x-axis points. Let me go back up to I'm going to get the overall average. For all groups. So it's 8.74. That's the mean. I'm going to try to remember these. 7.6 is for the median. And we can look at mode, which is our most frequent value. Or in our case, the should be the peak of that distribution. So it's 8. It's about 9 for the mean, 7 for the median, and about 4 for the mode. So I'm going to put those points in box 20. I think it was 4, 7, and 9. Okay. So this gives us an idea of how this distribution compares with the mean, median, mode of the overall estimates for those 8 disease groups. Okay, so something I really like about using Shiny for this is that I can compare different data, actual observed data, with distributions. Distributions from other groups. So right now we're looking at the real data for ARF and the posterior estimates in our predictive check for ARF as well. But what if I want to see how this compares with COPD? We knew that was a big difference on their days. Okay, so the data is, the shape is the skewness, or the fact that we do have a high level of skew is similar, but we see that distribution for ARF, which is in orange, which is our predicted distribution, that kind of exceeds a lot of that data. So we see that orange doesn't fit like a glove on our COPD data. So that orange reaches out further to the right using ARF's estimated distribution, doesn't fit that blue COP data. So we're expecting ARF to be, wow, that's a lot bigger. ARF has a much bigger, well, we know they have a longer lengths of stay, but we can kind of see how that distribution looks different as well. Okay, so you can do that. So let's go to, just out of curiosity, we'll go to CHF. Yeah, it's a lot. CHF is really just on, most of theirs on the low side. So so I guess the point that I wanted to show is, if we're thinking about length of stay from the ARF lens, it's not going to really apply to our different disease groups. So in this case, we should think about different distributions. And that's the benefit of hierarchical estimation, is that we can get more accurate results. And it helps show that not every group's going to be about the same. So we need to think about things differently when it comes to our disease groups and length of stay. I think it's easy to get kind of focused as whatever area I'm working in, that's how it is for everybody else. So if I'm someone that treats ARF patients, or if that's what I'm focused on, you definitely want to think about how each group differs, rather than, you can't use the one size fits all approach, in other words. So let's go ahead, and since CHF looks kind of interesting, we're going to go ahead and get we have the data up, but we need to change the parameters in 6 and 7. We're going to change that over to 3, mu of log y brackets 3. 3 would be CHF. It's the third group. And so we're going to get the sigma. Okay, so that fits a lot better. And then those red dots, those red plus signs gives us an idea of the mean, median, and log of the overall for all disease groups. And actually, I'm going to change the y limits. 7. Change that to 9. Okay, so now we can see how well that we can check our posterior to see how well our predictions, our predicted orange lines, fit the actual data. Okay, so that fits pretty good, and it definitely fits a lot better than if we used a normal distribution or a likelihood. So there's a big benefit to Bayesian analysis when looking at skewed data. Oh, I forgot we can add the legend. So I clicked yes in box 24. And that's about it for that. We can switch in box 25, we can switch it over the location of the legend, if you like it right in the middle on the right side. Okay, so this covers our normal, our log normal. I'm going to switch back to right now I'm going to look up for another distribution. Okay, so for our next sample, we're going to look at that trend line from a regression. So I'm going to use I'm going to use Kruschke's family income data. See what the trend is between family income and our family size and family income. I'm sorry, I'm just getting the file, the data frame names. Okay, so let me go back. Okay, so we're going to go load a new data set. Go back to the model builder. I'm going to type in HData, and I'm going to go to the very top of the Bayesian tab, and I'm going to put in the Coda object name. Okay, so in this you'll notice that we have beta parameters, and we have quite a few. We have it for, so in this data set we're looking at the average income within different states. So we're going to have 50, we're going to have, it also includes the 50 states and Washington, D.C. and Puerto Rico. So we have 52 parameters. You can see Z beta for JAGS, which I did it in. You need to standardize your coefficients because there's a strong correlation between your intercepts and your slopes. So a way to deal with that is to standardize your data, or standardize your parameters, and then transform it back to its original scale after or during that that Bayesian run. So we can see just from that first parameter, and the rest are going to be about the same. Good signs of convergence, high effective sample size, low shrink factor, low Monte Carlo standard errors. Standard error. And turn 19 off for now, right now. Okay, so from number 1, we're going to go down to OLS linear. I did something analogous to an ordinary least squares regression. In terms of polynomials, I'm at the linear or a first degree polynomial, which means just a straight line. I'm treating it as the trend as a straight line. The outcome is income. The group variable is family size. Click no for now. And we're going to go to the overall estimate, which I believe is beta. Rather than scrolling down, I'm just going to start typing in. Actually, I'm typing in at the wrong spot. So we should actually go down to step 9, 10, and 11 now. I have to go back to step 3. I need to put in the state ID. So I'll keep box 2 as the same. Our outcome is income. The group, our hierarchy is based on the states. And we're going to go to number 9. Our regression predictors, we only have one, and that's family size. Right now it's income regressed on family size. For our parameters in step 10, this is where I was looking for beta 0 mu. That's our overall We're going to do now beta 1. That would be our first beta coefficient. It's our regression parameter. And let's see, I think we can just go down to, I'll actually have to change I'm going to change some of the limits that I added in box 19 and 20 from our last example. I should probably shrink that a little bit. In box 18, add in points. You can actually, for this part it doesn't, there isn't a need to add in points, so I could leave that as it is, but I just want to clear it since I'm at a different example now. And for 24 we're going to take the legend away. Okay. Predicting by the group. We're predicting in our hierarchical estimation, we're adjusting for different states. Ooh, I can't really see what's going on there, so I'm going to change the line color. And I'll make it, I'm going to go with magenta, actually. And right now we have red dots and lines for actual data. So I'm going to try, I'm going to go to box 23 and I'm going to change that to thistle. That's not bad. Maybe I'll change the lines over to blue. Okay, so that, you can see it a little bit better. I'm going to increase the number of our posterior lines. So overall we can see an upward trend, and we can see that with the actual data. The blue lines represent our posterior estimate, and the thistle, or is someone violet colored dots and lines, represent the actual data. So that would be all 50 states plus the 2 other regions. And so now we can look at each individual state. We answered 4 for yes already. We actually probably don't need to use number 4. I think we just start entering the state. Well, we should do that to generate which state we want to look at in number 5. Take it back. So answer yes in box 4. Select the state you want to add its data to the graph, and then we go down to 10. Our Alabama is our first state. So we're going to put in the intercept, the beta 0. We'll add in beta 1 as well. And then for number 11, the trend data that we're going to add, the actual observed data, we're going to change that over to unit. It's actually harder to see now, but let me change the colors. Change the dots to blue. Okay, so we can see that that data, for the most part, matches up with our straight linear trend. But you do see in the actual data that it kind of peaks around 4 family members. That's what's on the x-axis. And then it drops So let's go ahead and go to our quadratic model. So let's go back to the model builder. We're going to type in HQ for hierarchical quadratic data. And we're going to go to the Bayesian tab and add a Q in there as well. Okay, we're going to go down to our posterior predictive check. We're going to click no on 27 right now just to avoid the error messages. We're going to go to box 1, change that to OLS quadratic. Box 2, the outcome is going to be median income. That's the median per state. Our grouping variable is the state, so we'll click on state ID. We're going to click no for generate levels, and I think I could actually, for number 4, I think I could have left it as yes and it would work because we're only looking at certain parameters. But go back, if I go to box 9, I'm going to put in the family size variable we used before, but we're also going to use the squared term, and that's family size 2. And now we're going to go and type in our parameters. It's beta 0 for our intercept, beta 1, that's for our family size coefficient, and now beta 2, that's the squared, that's the beta for our squared term. For number 11, I'm looking at all data, and I'm going to go back to 27 and now change that back to yes. Okay, so let's just change these colors again. I'm going to change blue to cyan. I'm using that color. Okay, so that's easier to see. And you can see the curve, that nonlinear trend we're looking at. You see that seems to fit the data better. So we have a better model by using that quadratic term, and we can visually inspect it by going to our posterior predictive check. So let's just take another look at Alabama. I'm actually going to leave most of it the same. I'm going to go up to number 4 and generate the levels. It's showing Alabama right now. I'm going to go down to 11, change that to unit. Okay, so we can see Alabama's actual data on their median income, and you can see it's slightly below the national average. And so I'm leaving in box 10, I'm leaving those overall estimates for the entire country. I'm leaving those in so I can get that. By doing that, I'm going to get the posterior distribution, the predicted curve for the U.S. In magenta, or I guess it's sort of purple or pinkish. So now I can just toggle. I can go up to number 6 and toggle between the different states. Let's go to Connecticut. And you can see in that blue line with actual data that their median income is actually above the national average, or what we would estimate as national average. Okay, so let's go back down to Alaska, which is actually going to be a little bit higher. And so to get the posterior predictive check, or I'm using it as a partial prediction plot, I'm going to click on beta 02, and I'm going to go to beta 1, which is family size, bracket 2, and for that squared term, okay, so you can see that fits nicely with Alaska's estimated posterior distribution with the actual data. I'm having a little trouble seeing the actual data, so I'm going to switch that over to, let's try spring green. That's a little bit better, but let's try yellow. It's a little bit better, but let me go to box 18, increase the XY label size. Okay, that's, let me just try blue, regular blue. Okay, that's a little better. But we can modify the plot as I showed earlier. This is our last posterior predictive check. We can add the legend, of course. You modify the graphing space. But that looks like about it. That's that. But you can definitely tell the improvement by adding that quadratic term. And that's the benefit of this section, is that with the posterior predictive check, you can check to see if your if the results you got really do kind of fit what's going on with the data. Okay, so now we're going to go. Now we'll go to the look at our hierarchical model more, and we're going to create a summary of our posterior distribution that we'll later use in a graph to highlight that data. I need to load some data, so I'm going to go to the Data tab, Browse, Examples, Shiny tab, and we're going to go to our baseball example. It's a really big file. Actually, it's too big for me to put in GitHub. I do have a smaller version of this file where I ran fewer steps in my chains. It doesn't give you the same results, but it gives you the same idea. The estimates will be a little bit different, but it's something that would work just to test out that data. Okay, so whoops. We'll type in the data, which is batting average. So in this example, we're looking at the batting averages for different players in Major League Baseball in the year 2012. So we have a 3-level model in which we have hits or at-bats nested within players, and those are nested within player positions. So those are the different levels that we have in our data. So go to the Bayesian tab, and we'll put in our Coda object. And let's see. We'll just go over one of the diagnostics. It's a big file. Because it's a little harder to estimate those higher level parameters, I had to use a lot of different I had to sample a lot of different steps in my simulation, so that effective sample size is about 48,000 for one of the lower level estimates. Let me go to Okay. Let me go to the overall average for all our different positions, which is at our highest level. And so that's about 30,000. Some of the other parameters that I used at that high level won't be as high, but yeah, it's a really big file. Takes a little bit more space to run 3-level models, but you get a lot of very rich information out of it. So let's go back down to the hierarchical model, create a summary of the posterior distribution. We're going to go to this section here, and we're going to specify that it's a 3-level model. And I'm going by the nomenclature of from hierarchical linear modeling that you might see in Breich and Raudenbusch, how they refer to their terms. So our outcome would be hits. Our level 2 group would be players in box 3. In box 4 we see our level 3 category is prior position, our primary position, theta name. So I use theta and omega to describe the lower and higher level parameters for center or average. So of those parameters, they'll begin with theta, and then in brackets we'll have it for each different player or position. So omega, and I need to go back to get that name. Okay. Okay, so that level 3 omega, the center for different positions, that would be the OMG OVR for overall. Okay, so I forgot to mention that we can choose the central tendency, and I have it on other sections. We can look at the mode, median, and mean of our posterior estimate. In some of the last examples, I looked at the mean, median, and mode of the distribution estimate. So you can convert, say in a normal distribution, the mean, median, and mode are all the same thing. So that would be a parameter that I'm estimating would be the mean, median, and mode. And we can see different values when we're looking at a log normal distribution, but we can select our central tendency that we prefer for each parameter that we estimate, and that could be the mode, mean, median, and mode. So that just means say I'm going to look at the omega estimate, and that's for the Greek symbol that's in that formula. I can choose the mean, median, and mean of that estimate, and they're all going to be very close. I would use the median if it's not a very high peaked estimate. Sometimes when you're using a uniform distribution, maybe you might get a parameter estimate that's a little bit on the flat side, but there is one random spot that's a little bit higher. If you use the mode, it's going to pick that, and maybe a parameter estimate that doesn't make sense. In that case, you'd be better off with the median. But mode is the most frequent, or in your distribution, it would be the highest peak spot. So I generally go with that. But I do have a box like that in other spots, so just to let you know. So the distribution we're using is, I did do a binomial in the likelihood, but I kind of interchanged the two because they can reduce down to the same formula. So I'm going to select beta. I can select the credible mass, and I forgot to mention it earlier that in different spots I can do that as well. but I'll just leave it as 0.95. Is the data aggregated? Yes, I did the binomial distribution, which I needed to aggregate my data. The value that it's aggregated on would be at bats. So each player has a certain number of at bats. Maybe if one player gets 30 out of 100 hits, that 100 would be the value that we need to modify the results. So I'm clicking on at bats. That would be the denominator of my outcome in box 2. So we select that in box 12. I run the posterior summary, and it's going to take a little while to do this. So I clicked yes. So just to summarize, in box 1, we're selecting the type of model. It's a 3-level model. In box 2, we select the outcome, which is hits. Box 3, we indicate which is the level 2 grouping variable, and that's the player. So we have hits nested within the player that are nested within the primary position, which is in box 4, and that's our level 3 category. I typed in the name that represents the lower level average or center, which is theta. 5, 6, and 7 would represent some sort of parameter that indicates the center. So our next level 2 variable would be omega, and that would represent the average for our different players. And then in number 7, that level 3 omega is the overall average for our level 3 category, which is primary position. Selected mode as our central tendency. I'm using a binomial distribution of my likelihood, and then our the credible mass that we're looking at is at 95% highest density interval. Number 11, data is aggregated, and it's aggregated using at-bats in box 12. For box 13, I created that posterior summary, and for box 14, I clicked yes so that I can see it when it's ready. So because we have these values show up, that means that it ran successfully. So we'll place that back to no. And so we're going to now graph it. We're going to sort this numerically, and by that I mean the actual parameter values, rather than sorting the results based on the player name. We're going to sort it on their batting average. We have 3-level groups. I could view the 3-level groups. Right now I'm going to leave that as no because I want to look at the players. And then for number 3, view a subset. Hold off for now. We'll leave the default settings and go to number 19. We'll run the HDI plot. Okay, so we have a lot going on in this graph. We have all the players. There's actually hundreds of players, and I think 150 or between 150 and 200 players in this data set. So on the left side we have the player names. The right side we have their estimated batting average. The empty or the hollow triangles represent what their batting average was in 2012, and then the more solid red triangles, which looks like a vertical red curve, that would be what we're seeing with sorted in the middle, those blue lines, and it's really just looks like a red and blue blob right now. But those are the highest density intervals. A lot of players, we see that since there are a lot of hollow triangles, we do see some players getting really high batting averages. And let me add the legend, since that'll explain it a little more. The observed rate is in that hollow red triangle. The solid red triangle represents the hierarchical estimate. So you get a lot of shrinkage going on. So those very high and very low batting averages are getting pulled towards the center. That's this gray line. That's the vertical gray line down the middle. And since there's so many players, what's probably going to help is if we look at actual players. In 2012, the World Series champions were the San Francisco Giants. So we'll go ahead and look at those players. I have kind of your starting 9 lineup during the year. I'm going to try to remember them as I place that in there. Okay, so I'm going to start typing in the name. I'm going to actually, in box 3, I'm going to click yes. Okay, now I'm going to start just typing in the name. So I'm just typing in the names for 9 players. Okay, so we have 9 players. Okay, so now we have the results for the starting lineup of the San Francisco Giants, who won the World Series that year. And in box 11, we're going to answer yes. And that's going to give us the overall average for our 9 different positions. So we can kind of get an idea of if these different players exceeded the performance that we saw that year. And what you can see is for their estimates, it's getting shrunk. Like Barry Zito, his batting average was a little bit lower than what you might expect for his position. So that gets pulled over to that to the middle area, to that gray vertical line, which represents the overall average. But you begin to see that for at least 5 players, their batting averages kind of exceeded where we might have thought they would have been based on individual players and taking into account the player position. Each of these different players represent different positions. So you do see a few players that did bat above average for when thinking about all the different positions. Okay, so let's remove our subset. And now we're going to go up to box number 2, and we're going to look at the level 3 groups, which would be position. And so you have pitchers, catchers, shortstops, left field, second base, first base, third base, center field, and right field. They're sorted based off of their average for their different positions. And these little the little plus signs that we see listed would be averages for different players in that position. So you can see for pitchers, most of the pitchers are kind of on the low end. And you can see heading up to right field, there's a greater concentration of pitchers, and they tend to be right around that overall average. And we might ask the question, well, does one position out have a better batting average than others? And you can use this to say yes, and you might in your data get extreme cases where you have a player with a 100% batting average but probably had very few at-bats. But this graph just gives you different ways of looking at the second and third level, and it takes into account differences between players and commonalities in positions. Okay, so in this we can also set in target lines. 0.3. So we can take a look at, well, could we ever have a position that could reach a batting average of 0.3 or 300? I'm just going to increase the size of the objects and font. What we don't have in this graph is we don't have a position for designated hitters. It's only in the American League, so only could affect about half the players. But no, probably for this we can see that that's beyond what we'd expect for our different players. I will come back to this in a second. Let me see what else we have on here that could be helpful. We have the legend. I'm in box 18. I will increase the line width. So it's really just the two vertical lines that we see here. We can change the x-axis limits in box 13 and 14. But we've covered pretty much the main parts. So we're going to go on to the predicted probability greater than a specific value. Okay, so in this section, the predicted probability greater than a specific value, what we can do is use our posterior distribution to calculate the probability of for certain values, as well as get the percentiles to figure out what would be about the average. So for example, we know the average is about 0.23 above in the baseball example, but maybe if we wanted to know the 25th, 50th, 75th percentiles, or even the first and the 99th percentiles, we can calculate that as well. So we're going to look at, for box 1, we're going to select our center parameter, and we want to know what it is for the overall average. Earlier we mentioned that we didn't have the designated hitter in that data. So let's calculate what are the chances of, if we did classify a designated hitter position, what are the odds, or what are the probabilities of their batting average being about 300. So in box 1 we selected the omega overall as our center. Now we're looking for predictor on spread. There's kappa. Kappa is our concentration. So And that formula for to get the shape and rate parameters, you can use your omega and your kappa, your center and your spread, to calculate the mean or the median. We're going to use a beta distribution. Leave 4 as the mode. For our y values, we're interested in a batting average of say about 0.23, which is the average above, and we'll use it for 0.30, which would be maybe that ideal of what a designated hitter could hit, what their batting average could be. So we're going to get the probability of reaching those probabilities, and then we're also going to see what is the various probabilities. So we're going to type in 0.25, 0.5, 0.75, and we'll just go ahead and put in the 5th and 95th percentiles just to see what we get. And we'll run the probabilities now. It's going to take a second to calculate. We have it here. So to bat for a player, for the designated hitter, the probability of reaching 0.25, that's if we're willing to assume that this probability for all positions is a good estimate of what a designated hitter could be. They would have the same players in there, but they would just be in for one division. But the probability of a player position batting 0.23 would be about 55%, or 0.55 to reach. But to get up to 0.3 as a position, we think that's more about an 8% probability. So that's a really low chance that it would get that high. So what, as I mentioned earlier, we do have Cohen's effect size estimates. And so we get that in this next section. And this only gets calculated when I have two probabilities. So I have two probabilities listed above in box 5, 0.23 and 0.30. If I added one more or took one away, then it wouldn't calculate an effect size. It only happens when there are two values in there. But we see that going that far above the overall average for all 9 positions, that effect size is 0.846. So that's about 0.85. That would be a large effect according to Cohen's effect sizes. So now you have the percentiles for the 5th, 25th, 50th, 75th, and 95th percentile. And they range from about 0.15 to about 0.32. So they range on the lower end, and they sort of peak kind of high up. And then so that's what we have in these sections here. And then this last bit of data, we get the estimated mean, and that's 0.23, 0.236. So we're looking, this gives us the mean. The formula that I was talking about above, I'm actually calculating the mode because we're using the mode from the that formula that uses the omega and kappa does calculate the mode value, and this estimate gives me the mean. It's just that we can use different formulas to get the same values, so I can give us the estimated mean as well. I did forget to show one more example, which was from our posterior predictive check. I'm going to go back to load some more data. Okay, so I'm going to go back to the support data, and this time I'm going to use a t-distribution. It's a robust regression, so I'm not using the t-distribution as a t-test, but I'm using it as a the t-distribution which has heavy tails that allow us to deal with outliers. So anytime you use a distribution that helps you with to deal with outliers, that would give us what's called a robust estimation. I'm using a regression, but I'm going to just focus on the difference between the 8 groups. I could do it as a hierarchical estimation using a t-distribution, and it would give us very similar results. So for this, let's see, for these I used a smaller set of steps when it ran, so my effective sample size isn't that great. It's only about 5,000 for that first estimate. Let's see what it looks like for the mean. 2,000. It's not the best estimate, but I want to show just this feature of in the posterior predictive check. Okay, so I'm going to go to the t-distribution. The outcome is charges. The grouping variable would be the disease group. I'm going to click no for now. And so when doing this distribution, I only really need to click the first group, M1. So when it sees M, it'll know that for those 8, from M1 to M8, they're part of the same analysis, are part of the same display that we're trying to get. And we'll click on Y sigma. Sigma will be our standard deviation. That's our SD parameter. And we do have a third shape and rate parameter, and that would be nu, or V, for the t-distribution. So I'm going to go down to nu. Nu, that's the letter for the Greek symbol. And let's see. Just want to make sure I have it all. Okay, so it should be all there. Okay, I'm going to change the color real quick before I start explaining it. Sound for the line color, and we'll use for the point color we'll use cyan. Okay, so what's nice about this is in this analysis I allowed for unequal variances. So generally, if I just allowed for equal variances, that spread that you see, say, in that very first the distribution on the far left would look similar to what we're seeing in the rest of these. And that probably would be under that middle above comma. That's probably how it might look if we allowed equal variances for all the different disease groups. But because I know that since we saw earlier, the acute renal failure and multiple organ system failure with sepsis had a pretty broad range in length of stay. And since going back to this data set in the 90s from 1995, the biggest link between hospital costs and hospital, or the biggest determinant of hospital cost was usually the length of stay. So not surprisingly, the ARF, which had the longest length of stay, also has the biggest cost. So I allowed for unequal variances so that we can see how much they differ. And what I like about this display is from John Kruschke's book. It's actually, for me, it's a little bit easier to see the differences between these groups when they're presented sideways like this. I'm just able to pick it up faster. So I added this. You can look at this as a normal or the log normal option in the in box 1 for the posterior predictive check. But I really like the display, how it shows it sideways, just so I can see the difference in variation between each of these different disease groups. They kind of spread out far, so I'm going to change the x-axis limits, or I'm sorry, the y-axis limits. Since it's sideways, it's the y-axis. I'm going to change that down to about 400,000. Okay. In fact, 300,000 might be better. Okay, so we can see the spread a little bit better. And why we call it a robust regression when we use a t-distribution is that these tails can really stretch out further. The tails show up differently in a t-distribution than a say a normal distribution, and they allow for it to spread on the low end as well as the high end, and that's what we see a lot of outliers, especially in that ARF group. And when we look at COPD and CHF, which we saw had narrow distributions, we see that here as well. So just by adjusting for these things, like the variance in the distribution and allowing for outliers, doing hierarchical estimates that take into account not just something at the patient or the in our last example, a baseball player's individual information. We can take that higher level information about their player position. We can add in all of these different things to get better or more accurate results. And so I think that's the benefit of that, and I think these displays will help with that purpose. But yeah, that's it. That's the last part of the last thing I wanted to show. I'll put in all the links I mentioned earlier. I'm going to put in my GitHub page that has the Shiny app as well as the location for the data that I used. The batting average example it was just too big to put into GitHub, or from my version to GitHub. So I have a smaller version, or with fewer simulations in it that could allow you to try it out. So I hope this is helpful, and hope that this work will be useful. I'm going to add more things to it, so please feel free to check back to see if there are any additions to it, and there will be. So thank you.